Hi, Michael.
Hi, Charles. How's it going?
It's going quite well. How's it going with you?
Not too bad. What are we going to be talking about today?
Well, what does the screen say?
It looks like a Wordle.
Yes, it's a Wordle. It's generalizing. And the key words are
Abstraction, scale, search.
What we're going to do is I'm going to try to jump off from some of the discussions that we had earlier that you led about generalization and try to sort of hop up a level above that and talk about abstraction and scale and search and sort of the things that make machine learning and reinforcement learning in particular hard.
Okay, but it seems to me that I talked about function approximation and everything is function approximation. So why is there more to say?
Well, we'll find out. That's the whole point of today's lesson.
All right.
Okay, so let's get going. So in order to elaborate on all of that, Michael, I want to ask you a simple question. And here it is. What makes reinforcement learning hard?
I'm going to say living on the streets.
Makes reinforcement learning hard?
Yeah, it sort of hardens it.
Let me ask that question slightly differently.
Oh, okay.
From a computational point of view, from an algorithmic point of view, what makes reinforcement learning hard?
So, well, there's a lot of things we've been talking about. There's the notion of delayed reward is a very tricky thing.
Oh, I like that one. Yeah, I like that one enough. I'm going to write it down.
You're not going to wait?
No, I'm not going to wait. I'm just going to write it down right now because it's ironic that way.
And a related issue, well, there's two pieces of that. There's the delay and there's a reward. The reward part is like, unlike, say, supervised learning, reinforcement learning is trying to do its job based on very weak feedback. That it's only told how it's doing and not necessarily what it should be doing.
Right, which makes it very different from normal function approximation in the way that we think about it in supervised learning. Okay, what else?
If we do try to use something like supervised learning, one thing that makes the function approximation hard is the idea that it's kind of a moving target. We tend to base our estimates on our current estimates as opposed to anything kind of legitimately valid in the world.
Right, so doing estimates based on estimates is a lot like averaging averages.
Okay. I want to say bootstrapping is the issue.
Yeah, I agree with that. Bootstrapping is sort of a problem. I think I would probably summarize that as the problem with the need to do good exploration. And that's a little different from the normal supervised learning setup where you've got a bunch of training examples. Here, because you only have estimates in the reinforcement learning context, you have to do a bunch of extra things to actually figure out how to get good estimates so that you can actually do good learning. So one more thing, I think, sort of worth mentioning, that makes this sort of hard, and it's kind of very basic kind of computational problems, right? You know, when we describe computational complexity, we talk about it in terms of big O, and the question is big O of what? So what's the what here? What's the in our big O that makes R hard?
Well, there's a lot of them.
Like what?
Well, I mean, if we're thinking about sort of MDP style reinforcement learning, then the size of the state space is a big O.
Mm-hmm.
The size of the temporal window in some sense, like how delayed is the reward.
Mm-hmm.
There's issues on, well, it could be the actions as well. There's lots of things that could scale. But I guess what makes state super hard is that you can very easily specify a problem that has a state space with an exponential number of states that is still relatively simple, but algorithms that don't generalize between states are not going to be able to learn in them very effectively.
I think all of what you said is true. Some of it, I think, is kind of captured, though not necessarily explicitly in the first two bullet points. But I'd like to focus on states and actions. That the problem is that the learning that we need to do grows superlinearly in general. We aren't very, very careful and smart in the number of states and the number of actions. And so we really need to have kind of clever ways of thinking about learning across multiple states and perhaps multiple actions. And in fact, when you talked about function approximation and generalization, I would claim that, at least in sort of this discussion, we could talk about that as a way of dealing with generalizing over states, that you did function approximation over value functions, right? So here you tried one way of dealing with the problem of scale when it comes to states is, well, if I learn something about one state, I want to somehow have that teach me something about a bunch of other states. And then I won't have to visit every single state, an infinite number of times and take every action an infinite number of times. And that's really good. That's really important, right? And the trick here is I can see many, many states by just seeing a single state. And that's what function approximation over the value functions actually gives me. Agreed?
Yeah, I don't know that I would say it quite that way, but that we learn about many states when we learn about other states or something like that. But yeah, no, yeah, that's absolutely the way I was thinking about function approximation is helping us to kind of fill in the gaps for states that we haven't visited nearly as often.
So, in fact, I could be aggressive and ask you the question, why did you do all this function approximation over states, but you didn't do any function approximation over actions, Michael?
That would be aggressive. And the I don't have a wonderful answer to that. I mean, it's tradition in the sense that a lot of the MDPs that people have been working with really do try to keep the action space relatively small and expand in the state space, but that's not really that good of an answer. I think large action spaces are really important too. We just don't have as good ways to deal with them. For one thing, the computing the max ends up being hard in Q learning.
Right. So, in fact, what I'm going to try to talk about in the rest of the lesson is trying to do generalizations of the sort of generalization that you were talking about and think about how we can learn about actions and how we can abstract over actions in the same way that you were abstracting over states.
Oh, that seems great and a little bit meta.
A little bit meta. And so that's why the lesson's generalizing over generalizing. And the whole point in the end, I'm going to claim, other than just sort of it's interesting in and of itself, is that it's going to allow us to scale. So all of these tricks ultimately have a kind of practical use, including function approximation, of allowing us to scale. Okay, Michael, so to demonstrate this idea, or to demonstrate some of these ideas, I'm going to look at grid worlds. One, a very simple grid world to try to get across a pretty straightforward idea, at least what I hope is a pretty straightforward idea, and then a slightly more complicated and prettier grid world in but a moment. But first, let's look at kind of a basic grid world. So this is like our famous 4x3 grid world, except I've added a couple of details. I haven't drawn all the little squares and all the little tiny grids because really I just sort of want to pop up a level here. But you start somewhere in this world, it almost doesn't matter where, and you have to try to get here to the little +1. That's where all the reward in the world is. And you have the normal actions. You can move up, down, left, right, and it's slippery. So every once in a while when you try to move up, you end up moving in a perpendicular direction and the usual sort of thing that we normally do. Now, other than that, what's different about this world is that I've got walls like we had before, except these walls actually happen to coincidentally create little rooms. So let's imagine that you're starting over here somewhere, and your goal is to eventually learn in this world how to get to, well, this goal. So I think we know how to do this. I think we've done this before many, many times. We certainly did it in the 4x3 grid world. But I want to ask you a slightly different question. I want you to think about this in a slightly different way. If you were trying to tell a person how you should get from this point to this point, what would you tell them?
I'm going to say Google Maps.
This isn't on Google Maps. This is in a GPS dead zone.
What?
Yeah, I know. It's amazing.
Wow. I guess that's one of the real benefits of reinforcement learning is it can work even in a GPS dead zone. So so the question is, how would you tell them to go? Well, so, we talk to agents via policies. So I could try to give a policy, but you didn't really give, so that's a mapping from states to actions, but you didn't really give me a lot of details about what the states were. So probably if I was talking to a person, I would say something kind of high level, like, well, pass through the doorway to the east, then you enter a room and there's a doorway to the south, go through that, and then a little bit inside the doorway, you'll find a great reward, or at least a reward.
+1 is the greatest reward that anyone can receive, Michael. You know that. So, right. And I like this because what you did is I gave you the actions up, down, left, right. And you could have said, okay, so move right, down, right, and then go, I don't know, right, down, right, or something. But instead, you said, well, go to the doorway, and then go to another doorway. And then once you're past that doorway, you'll just take a couple of steps and you'll end up where you want to be, where the great reward is. And that's perfectly reasonable. In fact, it's more than perfectly reasonable. It's a kind of abstraction. In the same way that function approximation is a sort of abstraction over the states, what you just described is what we call temporal abstraction.
Ah, I see.
And that has a specific meaning, but I think to really kind of grasp what it is, the right way to think about it is you came up with new actions.
That's making the action space bigger.
Making the action space bigger, which is a problem you would think, but each of these actions actually covers an enormous amount of ground. So in fact, if you had said right, down, right, down, 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 right, or something like that, that's a lot of actions to have to reason over a long period of time. But what you actually said was take one action, take another action, and then, I don't know, take one or two actions. So we managed to do with your new actions in, I don't know, about 5 steps, what would have otherwise taken, 100 steps. Or maybe
that's a cool idea.
Maybe 60 steps, right? And that is where the abstraction comes from and where the temporal nature comes from. Because again, the one of the things that makes reinforcement learning hard is this delayed reward, and what's implicit in that is that you have to reason over time, that you have to take many, many steps, and because all the there are several options at every state, you're actually getting an exponential blow up over all the paths you might take. And here what you've done is you've traded off the price in adding new actions with being able to skip over having to make a bunch of decisions along the way. And so now I can do in 5 steps what would have taken 100 steps, and that's going to be a gigantic exponential savings. Does that make sense?
Yeah, and I appreciate you giving me credit for thinking of this idea, but the reality of it is you kind of forced my hand by not like I couldn't have said right down because I don't see the low-level grid positions. So I don't know if it's 100 or 1,000 or 60 or anything. But cool. I mean, that gives me credit for something that I don't really deserve.
Well, but I did tell you that you could go up, down, left, right. If you had said, well, I tell you to go right, I just would have moved right a little bit and you would have seen where I was and you would go, oh, you got to keep going right, keep going right, keep going right. And yeah, I could have made that as granular as I wanted to, but it has to be fairly granular or there's no way to get from here through the doorway, through one of the doorways, which you absolutely have to do. So let's be a little bit more concrete. So let's write down exactly what that action was. I don't know what it is, but you created a bunch of actions that I'm going to say are things like go to doorway. And we can even name those doorways. Let's call them X. And so that would be 1, 2, 3, 4 more actions, which are going to allow me to save possibly many, many steps. So let's think about that. What if I had started here? What would you have told me?
Well, in principle, the plan that I gave you could still work. This go to the doorway to the east and then go to the doorway to the south.
Right. And by the way, well, go ahead.
Well, it seems like the room layout that you have makes it possible to go the kind of the southerly route as well.
Right. There's some point where going east and then south is not as good as going south and then east. So, and I don't know exactly where that point is, but I'll make it easy for you by drawing a dot there. What would you tell me to do there?
I would totally tell you to go east and then south.
Right.
So east to the doorway, south to the doorway, then down.
Right. So for a whole bunch of states inside of this room, no matter what I do, the action is the same, even though I'm in different states. I should still just go here. I take one action for one particular state. So the plan itself and sort of what I'm searching over is actually much simpler. And that would be true for, I think, probably any space inside of this room. Your answer would be?
Just go to the south door.
Right. And, not to drive the point home too much, but what about from here? Well, I think it's obvious you tell me to go here. From here, you tell me to go here. From here, you tell me to go here. At some point, there's a switch off between whether going through this door or going through this door is the right thing to do. But there you go. And then once you're in the room, well, then you're going to have to take, sort of baby steps towards the goal. But regardless, I'm going to claim that this is an easier kind of space to reason over than having to live in the original action space. Notice I've changed nothing about states. I've said nothing about function approximation over states. I'm talking about abstraction over this set of actions that you have.
Well, you did implicitly talk a little bit about states when you said that all the states in, say, the northeast room end up being sort of equivalent.
Right. Equivalent with respect to the action that you want to take, yes.
Yeah.
Right. Which is its own kind of approximation, its own kind of abstraction. All of these are different kinds of abstraction, really.
Okay.
And will allow us to do scale. So let me just add one more thing to this before we move on to the next slide. And what I want to point out is that this isn't just a way for you to think about this problem or to sort of in a compact and efficient way explain how you would accomplish a particular goal. It actually has other computational benefits. So if we think in this sort of southeast room here about how value propagation works, right? You took a bunch of actions in here, you got to this good space, then you start backing up values, right? So I know this is worth a lot because 1 is the biggest number in the universe without loss of generality. Assume 1 is the largest number. And then I'm going to learn that being in this state and taking this particular action is also good. I'll just draw a little dot here, the big size saying that's really good, and a slightly smaller dot and a slightly smaller dot. And so the value of the states around here are nice and big because I can easily get from here to the goal state. And as I move farther away, the value gets to be, a little bit less, and then a little bit less, and a little bit less, and it sort of propagates out into the other rooms. And the way that you propagate this information is actually kind of slow, right? You have to get to the state and sort of back it up a little bit. Your horizon is such that the value seems relatively small, and you kind of keep going. And you have to visit this often, very often actually, to back up the information to tell you sort of what the value of the states are, what the Q values of state and action pairs are. And that's fine. That's how we do that's how we learn in MDPs. But because I have this abstract action, I have this go to doorway, I can actually, from here, from this particular state at the doorway, back up information all the way to here, wherever it is I executed that particular action, in sort of one step. So I learn a lot about the value of being in this state immediately from having taken that and gotten here. So as soon as information from my little +1 box here gets me to here, I can back that information all the way up to where I initially executed the go to doorway X. And similarly, now that I've got information here, I can back it all the way up to the value of being in this state. And so I can back up information and value much more quickly without having to back it up sort of one little state at a time. So there's a lot of advantages here, sort of computational and otherwise, that will hopefully allow us to learn faster.
Cool. And I think that's helping me understand why it's temporal abstraction, right? So state abstraction is treating a whole bunch of states sort of equivalently. This is actually treating a whole bunch of time steps equivalently, right? That we can just kind of elide over them.
Right. And now you'll notice that it will have this side effect of allowing us to treat a bunch of states similarly, because we know that for one way of thinking about similarity between states is sort of how their features are similar to one another. That's what you talked about. Another way to think about similarity among states is to think about whether you should take the same action when you're in them. And so every single state in this room is the same in the sense that the optimal action is the same. Go to this doorway. We're going to make all this little hand-wavy stuff that I did, which I like, a bit more concrete, which you should appreciate because I'm making an abstraction more concrete. Thank you very much. I'm here all week. In order to do that, we're going to actually introduce a real formalism called options. And options are just a way of writing down explicitly what we mean by this temporal abstraction, new actions idea.
Okay, and is this related to concepts like the financial version of options, like stock options?
I'm going to say no, because I've never really understood those things.
Oh, so maybe they are related.
Probably not, though. I'm going to say that options are just a fancy way of saying choices. It's a fancy way of saying actions. Here's what an option actually is. So an option is a tuple, because everything in life is a tuple, and it has 3 parts to it. So in fact, it's a triple. It has I, which is the initiation set. It has pi, which is almost always the case, a policy. And then it has beta, which is a termination set. So let me explain what I mean by those things. So the initiation set I is just the set of states where the particular option or super action, like go to doorway in the south, is actually legal to be executed. So this is where it may start or initiate. So there's a set of states where an action actually makes sense. So let's take your action, which was go to the door to the south, right? Mm-hmm. So that's clearly legal inside the northeast corner. But I think the way you meant it anyway, it's not really something that you would execute from, say, the southwest corner. Does that seem reasonable?
Yeah, I feel like it sort of violates the spirit a little bit. If it's the case that you can navigate to that south doorway from anywhere, then why not just navigate to the goal from anywhere, right? We're not really breaking it down into simpler subproblems.
Right, exactly. So in fact, we should just have one action, which is solve the problem.
Right.
And you should just execute that. That's going to be at least as hard to learn as the original problem, and probably as hard to execute. And if you already had that, then there was nothing to do in the first place.
Is the aesthetic here sort of like, I don't know, algorithm design in computer science, a sort of idea that you want to break a problem up into subproblems, but somehow have solved a little bit of the main problem along the way? I'm thinking of things like, I don't know, quicksort and merge sort and so forth, where you recursively solve the same kind of problem, but it's not cyclical. It's not like you make no progress, because at each time you break down the problem, it actually makes it a little bit easier.
Right. So in fact, I think the word abstraction here is quite important. We do abstraction when we code, right? We create functions, and then we use those functions to think about the problem at a more abstract level, and it allows us to solve the problem more easily. And so so I think that's a pretty good analogy. It's not a perfect analogy. There's not really an input and an output here, but it's trying to solve the same idea of modularity and reusability, for that matter. And it allows us to make the problem easier to think about and easier to solve.
Cool. I like how computer science comes up even inside of computer science.
Yes, computing is everywhere. It is computing all the way down. So we have this initiation set. So that's places where it's, let's say, legally reasonable to actually execute this option or this abstract action. Similarly, we have termination sets. And a termination set is not the set of states where an option may be ended. It's actually a generalization of that. It's a set of probabilities. So it maps states to a number, which is the probability that the option will end in that state or can end in that state.
I think that makes sense. So they're both kind of sets, but this is kind of a more soft, general kind of set. And is it saying that no matter what, when the option gets to one of those termination states, a coin is flipped, and if it comes up heads, then the option's done?
I think from from the point of view of the person sitting outside the option, yes. Inside the option, it doesn't have to be quite done that. It's not quite done that way. It's not like the option is running and it's always flipping a coin. This is more sort of a way of describing the fact that something can end in a particular state. Now, of course, you could turn this into a set by putting a probability of 0 over all the states where you don't want it to end and having a probability of 1 exactly where you want it to end.
I see. So that's a sense in which it's a generalization of that idea.
Right, exactly. But basically, I'm going to execute this action starting from one of the states in set I, and it's going to run, and it will end up in some state when the option terminates, and this gives me a probability of it being in one particular state or the other. So all an action is, right, it's you're in a state, you take an action, and you end up in another state. But since we're talking about these temporally abstract options, things that happen over time, we need to know what's happening inside the option while it's running. And we already have a term for that, and it's called a policy. So here we have a generalization of the way we've been talking about policies anyway. Policy is more than, within an option, a policy is more than just a mapping from states to action. Here, it's a probability of being in a state and taking a particular action. But again, we could turn that into a normal policy, as we've mostly been talking about it, by just having a probability of 1 over the action that we're going to take and 0 over the one over everything else, and then it is just a direct, simple mapping from state to action.
Like a deterministic Markov memoryless policy.
Thingamajiggy, yes, exactly right. But anyway, this is a formalism, but I think it sort of is just trying to capture this idea of, as you say, kind of a procedure or a function that runs. There are places where you can execute the function. There are states where you will end up after you've executed the function, and there are things that are happening inside the function. The code itself is the policy. It's the actions that you're going to take and the states that you're going to see.
Okay.
Okay. So let's see what we can do with that. Okay, Michael, so enough of all this hand-waving you like to do. Let's actually write out some equations.
Okay.
Yeah, there's no need to fear the equations, Michael. So I'm going to leave our little picture up so you can remember what it is we're talking about. And I'm going to leave up the definition or the tuple part of what an option is so that you'll remember that. And then I'm just going to write an equation up here. And here it is. So v sub t plus 1 of s equals max over O of the quantity r of s comma O plus the sum over s prime of s of O, s prime times v sub t of s prime. What does that equation look like to you?
Well, it has a lot in common with the Bellman equation.
Right. And in fact, that's exactly what it is. It is a rewriting of the Bellman operator. So what do you think the various constituent parts are?
Well, maybe an easier thing to do would be to explain what looks like it might be different.
Okay.
So for one thing, A has become O because I guess actions have become possibly temporally extended actions.
Or options.
Or options. Good. Do we need to include A in there as well? Like why how can we ignore all the A's?
Well, because the A's are inside the O's.
The A's are inside the O's.
Yes.
There's actually an O inside an A.
Well, I think that depends upon whether it's a lowercase or capital A.
That's fair.
Thank you.
But I still don't quite understand. Like, so you're saying options are made out of actions.
Yes, because they have little policies.
But can you have an option that is just an action?
Of course, right? So options are a generalization of actions. If I wanted to take an action and I wanted to turn it into an option, then the initiation set would just be everywhere where that action is valid. The policy inside that option would just say, for whatever state I'm in, take that action with probability 1 and all other actions with probability 0.
Mm-hmm.
And then the termination probability would be 1 for all of the states that I can reach from that particular state to a particular action. Actually, it would just be 1 everywhere.
1 everywhere. I see. Oh, that's okay. That's actually really cute. That kind of helps me understand why these 3 quantities are the way that they are. So it allows us to specifically say, oh yeah, well, we can always include an action which is a primitive action that just, you can use it wherever you can use the action. It just does the action and then it stops right away.
Right, exactly.
Okay. All right, good. So then the O, okay, I get the O's generalizing the A. Then another difference is there's no discount factor that I can see. And then the last difference is that you seem to have spelled T as an F.
Right. Well, F and T are the same for an appropriate kind of thinking about.
Only in logic.
Only in logic?
Yeah, T and F are the same.
Actually, they're the opposite in logic.
Oh, whoops.
Yeah. T is true and F is false. I hadn't thought about that. That's kind of a interesting thing that we could talk about for an hour and a half. Or I could just explain to you what F is. So you did the right thing. You noticed that we still have a reward function as we did before in the Bellman operator. We still have value functions. That's what we're trying to do. We're trying to update value over states. We have the little S's and the S primes. The O's are basically A's, so that doesn't seem different. But the 2 big differences are a lack of a discount factor, which isn't quite true. We actually have a discount factor, but it's hidden. And instead of a transition model, we have F. So F is, if this really is a Bellman operator, F is sort of, I think, clearly playing the role of a transition function. It's somehow telling you something about states, options, and next states. And what I really need to do to make this clear, I think, is to just really write out what F is.
Oh, that would be super helpful.
That would be really nice. But it turns out that I have to write out something else as well, and that is R. So R looks sort of superficially like the reward function that we've had before, although in this case the reward is from, taking a particular option in a particular state. But actually, this reward function is hiding a lot of complexity as well. And to see what that complexity is, I think it helps to draw a picture. So what have I drawn down here? So what I've drawn is an MDP and a particular trajectory through that MDP. So here the dots are states, and the little lines are sort of the actions that you took to move between those states and whatever reward you happen to pick up along the way. So I'm in some MDP, a Markov decision process, and I am moving through states, taking actions and receiving rewards, and I'm sort of moving through that. And that's kind of what we've been thinking about before, right? This is what the Bellman equation sort of captures for us. I'm going to be in a state, take an action, end up in the next state, I'm going to be getting rewards. I should accumulate all that and use that to update my estimate of the value of being in a particular state. Right? That all sound familiar?
That is a diagram of SAR, 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 SAR.
Right. This is SAR, 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 forever and ever. Now, we know how this works. One of us, probably both of us at some point or another, actually sort of explained the math behind here and how you would back up values and why this is a way to do learning. But in this space where we have these temporal abstractions, we have these options, we're actually violating everything that we know about MDPs. And I think it helps there to draw a slightly different picture. So because we have these temporally abstract options, we are not having very simple time steps, right? So here, kind of implicit in this is we're in a state, we take an action, and then we're in another state. We're in a state, we take an action, another state, so on and so forth. And how much time passes between visiting each of these states? Michael?
I'm going to call it 1 time step.
1 time step, which I'm going to claim, you may not agree with this, might as well be the same thing as 0 time steps. In some sense, we treat the actions in an MDP as if they are instantaneous. And perhaps to drag on more of the computer science analogy, we treat them as if they are atomic.
Okay, I'm along with you for the atomic idea. I definitely am not along with you in the it takes 0 time idea. But I guess 0 time in the sense that there's no there's no crack in it. There's no window that anything else can jump in. And that's really the idea of atomic. So I think we agree.
Yeah, I think we do agree. I mean, you're basically, we're picking constants. You want to call it 1, I want to call it 0. We can both
No, but
claim each.
that's like me saying T and F are the same thing. 0 and 1 are not the same thing.
They're the same thing within a constant.
Not a multiplicative constant.
Fair enough. The point here is that in some sense, atomic, instantaneous, what really is happening here is I was in a state, I took an action, I ended up in another state. Nothing else can happen. We treat that time step, it may be a year, it may be a day, but whatever it is, we treat them all as if they're the same, and we're just moving along. In fact, we talk about time steps. And implicit, I think, in the way we've been talking about time steps so far is that they're all the same length, whatever they are, which is why you can call them 1 as opposed to 7. It doesn't really matter. The fact is that I take this, there's an atomic action taken, I end up somewhere else. Nothing else happens in the middle. I can reason about everything. By contrast, once we have these options, I mean, think about this this picture up here. Think about the the northeast room. If I'm in this little pink state here, I just entered into the room, I'm going to get from here, the east door, to the south door in some amount of time. Right? It's going to be made up of atomic actions because all I really have is up, down, left, and right. And I don't know how long that's going to take. Let's say it takes 50 time steps. It doesn't really matter. It's going to take some number of time steps. But if I'm in this little space down here near the bottom, already near the door, that's going to take fewer time steps. So what I'm actually seeing with respect to the underlying MDP is I start in some state, I take one of these options, some amount of time passes, often more than the single time step, and then I end up in another state. And then I take another option, I end up in another state, take another option, I end up in another state, and so on and so forth. And the amount of time that I spend in each option is variable, potentially, and is not necessarily at the same as the atomic actions that we had before.
Oh, interesting. Okay, so variable time steps.
Right.
So does that mess up everything?
It does, because if you think about the way Bellman works, is it assumes a discount that happens at every time step, and it accumulates information along the way. So we need to have a way to capture all of that that allows us to get all of the neat little features of an MDP while still allowing us to use these variable time actions. It turns out that's pretty straightforward to do. I'll just write out the equations for you, and hopefully it'll be easy to see. Okay, Michael, so here's the definition of the reward function S comma O. It's an expectation over the set of rewards that I'm going to see, discounted at each step by gamma. So the first reward that I see, R1, at step 1 is going to be R. At step 2, it's going to be R2, discounted by gamma. At step 3, it's going to be R3, discounted by gamma squared, and so on and so forth, until the option ends after K steps. And that final reward will be discounted by gamma to the K minus 1. So this is, in some sense, the average, in fact, in a very particular sense, this is the average discounted reward that I will see by executing this option in this particular state. Does that make sense?
Yes. I mean, I guess it's weird because it's kind of immediate reward in the sense that it's the reward that comes from that executing that one option, but it's also clearly not immediate reward. It's a sum of rewards.
Right. So one way of thinking about this is, remember, all an option is a policy that I'm going to execute. That policy will be realized in specific actions, which means it will be realized in particular states and rewards that I will see, a bunch of SARs. So even though from the outside I start here in this particular state, some time passes and I end up in this state, what's actually happening along the way is I'm visiting every single one of these states and picking up reward along the way. But we need to be able to discount that reward, and so the discount factor is hidden inside of the reward function. So this is as if, rather than executing the option, I had actually just executed all the atomic actions that the option itself will in fact execute.
And then you'll call that sort of one bolus of reward.
Right, because all that's really happening, right, is that whenever you have this kind of summation over you're seeing a bunch of states and taking a bunch of actions, all you're doing is adding up all the rewards you're going to see. Remember, we got the Bellman equation by just writing out that we're going to visit a whole bunch of rewards. That the definition of the value of being in the state is the expected discounted reward.
So, and we're keeping that consistent here in this abstracted, temporally abstract actions setting, by virtue of the fact that still the immediate rewards are discounted according to the true time steps of the underlying process, even though we, I guess, as the agent, get to think at a higher level. We get to think about an action taking multiple steps.
Right, exactly. And so we do something very similar for f, and we end up with this nice equation. So here's f, Michael. So just like I wrote r as an expectation over the set of rewards that you're going to see after k steps, I'm going to write f in the same way. And I've sort of got some really funky notation here, but let me try to explain it. In English, f is simply the expectation of me ending up in S prime after k steps. So this delta, because I can't draw lowercase delta as well, this is a delta function. It is 1 in the case where the kth state that I see is actually equal to S prime and 0 otherwise. And delta to the k is just, well, the discount factor raised to the kth power. So f is an expectation over, after I've executed the option, that I will end up in state S prime, having started in state S and having taken k steps. Now, notice, why do I even have to go through all this? Why couldn't I just put t of s, comma o, comma s prime here? Well, first off, t is defined in terms of a. It's not defined in terms of o, but that's okay. The reason I have to do this little funky thing and why we call it f instead of t is because, as you pointed out in the beginning, there needs to be a discount factor attached to the value of the next state, which in this case is s prime. So what we've done is we've rolled up that discount factor inside of f. So f is the expectation of me starting in S, taking option O, ending up in S prime after k steps, and the delta sub k gets sort of brought along with that expectation so that I can appropriately discount the S prime state that I will end up in.
Okay.
Right. So in the end, both R and F are just expectations. They're exactly doing what they were doing in the original Bellman operator, Bellman equation that we're using before. In the original Bellman equation, the reward was just the immediate reward that we got for taking an action. Here, the reward is just an expectation over all the rewards that we're going to see given that we've taken this particular option. If the option is, in fact, a single action, then it would be exactly the same thing as the reward we would get for being in that state and taking that action. Similarly, f is just a transition function, except now it's sort of the accumulation of all the transitions of starting at S and ending up in S prime after k steps, given that I took the particular actions that are inside of the option and defined by pi. Now, there's a couple neat facts about this, and I will write them down on the next slide, but I just want to point out what's particularly cool about this is that it really is a Bellman equation. It really does allow us to do all of the things that the Bellman equation, Bellman operator allowed us to do in MDPs, but it allows us to analyze or to reason about or to plan over this multiple variable time MDP. So in fact, this kind of MDP has a name, which I probably should have written down earlier, and it's called SMDP, where the S stands for, what do you think, Michael?
Something?
Yes, and that something is semi. So this is called a semi-Markov decision process, and the difference between the Markov decision process and the semi-Markov decision process is you get to make these jumps in time. And because we have this Bellman operator that takes into account all the possible jumps in time that you might take, in the end, it grounds out to an underlying MDP and allows us to inherit all the things that Bellman allowed us to inherit. SMDP, by the way, there's an entire literature about semi-Markov decision processes well beyond the sort of scope of this lesson. But from our point of view, what's really neat about this, and this comes up again and again when you use SMDPs, is that once we define an SMDP and the appropriate Bellman operator for it, we can basically just pretend that it's an MDP because at bottom it is an MDP, and these expectations allow us to ground out in that MDP. And so we can just pretend we're always dealing with an MDP and we only have to deal with the fact that it's an SMDP. It just works. I take an option as just an action. It just takes time and is an atomic, but whatever. I might as well treat them as if they're atomic. I just let it run and it comes back. And when it comes back, it will have accumulated for me all of the reward that I would accumulate if I were living in the underlying MDP, and it will discount the future in exactly the right way after I've taken k steps.
Woo!
Yes, exactly. So this is a lot of sort of equation writing and deltas and delta raised to powers and expectations that allows us to say, you know what, we're still dealing with MDPs with options. Everything we knew before works.
Okay, that's a relief, I guess, that we didn't have to throw all that out and start afresh.
Yeah, and again, I mean, it's actually important. This is, for me, this seemed like a subtle point for a long time, but it's actually not that subtle. It's just an SMDP is just an MDP, and where we have to keep track of the fact that our actions are not atomic and accumulate reward and accumulate all the transitions. But really, that's all captured very nicely by this expectation. It just means we have to hide things like the discount factors inside of our functions, whereas before with the MDP, we could stick them outside of the transition functions.
Okay. Well, I'm not quite getting the name, I think. Semi-Markov decision process sounds like it's, kind of Markov, but also kind of not Markov.
Yeah, that's right. It's semi-Markov.
But this seems Markov, right? I mean, underneath, it's just a whole bunch of standard MDP type transitions.
Yeah, that's exactly right. But what's allowing it, but at the level of the options, right, it's not Markov because you have to know how much time has passed.
Oh, I see. So the state that we end up in could actually depend on how much time we've spent, how much time has elapsed.
In fact, it will, in general, right? Because if I do it in one step, I'm going to end up in some state. I can't reach the states that are more than one step away. If I take 10 steps, then I can reach more states. So the state I end up in does depend upon K. It depends upon how long the option was executed. And in general, since beta is a probability over states, it could happen at any time.
I see. So it's got elements of Markov and elements of not Markov.
Right.
So elements of Markov include things like, well, we can think about the probability distribution over where we're going to end up. It really is Markov.
Mm-hmm.
But we have to be much more careful when we actually sum up rewards because the time that has elapsed is variable. And so we have to actually take into consideration how many steps have passed to do that.
Right, and how do we and in fact, that's a very important point, and I'll sort of point out two things here. One is, when we have a process that is not Markovian, often we can turn basically any non-Markovian process into a Markovian process by just keeping track of enough history, right?
Mm.
And history is often, time is enough. Sometimes you actually want to know what states you visited, but often time is enough. And so we can turn a non-Markovian thing into a Markovian thing. And in some ways, that's what we're doing here, right? We are keeping track of the places that we saw in between. But at the level of the SMDP, at the level of the options, I can ignore the MDP and pretend that the SMDP is an MDP and that these are really atomic actions. But in reality, they aren't, which is why R and F actually depend upon K. It actually matters how many steps you took, and that affects the expectation. And in fact, if you look at R, I'm actually accumulating all the rewards. So I'm taking something that's non-Markovian because it depends upon the actual rewards that I see, which depends upon the actual states that I visited. And I'm gathering them with me as I go along so that when I pop out a level, it goes back to looking Markovian again.
Cool.
Right. So an SMDP, it's an MDP, and I don't have to think about it anymore.
I feel like I'm getting the kind of math of this, but it's still a bit of an abstraction to me. Can we get into some kind of an example to practice these ideas?
So yes, first I want to point out that I appreciate the pun, using the word abstraction here.
Thanks.
Really good. I like that. But I think the answer is both yes and no. I'm going to go through an example that I think might help you think a little bit about this. But I also think that actually working out all these expectations would take us a long time, and it's a really good and useful exercise, which is why it should probably be an exercise. We'll let the students do it.
I mean, I don't know. It seems like a cool exercise in dynamic programming and algorithm design.
But Michael, you think everything is a cool exercise in dynamic programming?
Well, that may be, but that's because everything is a cool exercise in dynamic programming.
Yes, that's an excellent point, and why we're going to move on to the next slide. All right, Michael, so I'm going to deal with your request by trying to go through an exercise with you where we try to figure out what these options are, and there's going to be a secret point here that has to do, as always, with abstraction. So here's what I'm going to do. So we've got the same little grid world that we had before up here, but I have introduced another grid world. Do you recognize this grid world?
It looks like a very tiny little game of Pac-Man.
It is exactly a tiny little game of Pac-Man. So what I want to do with this tiny little game of Pac-Man, which again is just a grid world, is I want to explore this notion of options and see what we can figure out about them. So everybody remembers Pac-Man? So Michael, for the benefit of the audience that has never played Pac-Man, all 0 of them, why don't you explain to us how Pac-Man works?
Sure. So in the game, we're a little Jewish guy named Pac-Man, and we're running around in the grid. We're the yellow guy, and we chomp, 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 chomp. We can't go through the blue walls. We're being pursued by, it looks like sort of...
Careful.
Yeah. I'm going to go with French fry goblins from McDonald's. So as we move around in the grid, we consume those little dots the little pellets, and that gives us
Yep.
points. If we can actually clear all the little dots and the big dots from the screen, then we have successfully completed the screen and we get an even more exciting challenge next.
Yes.
But I want to say that there's one other important thing is that if we eat one of those power pellets, the big fat dots,
Yep.
then the tables are turned on our ghost friends, and we can actually, if we touch them, consume them. We get points, and then they have to I believe their eyeballs run away and regenerate.
Yes, that's exactly what happens, just like in real life. So, yeah, so if the ghosts touch us, we die unless we've had the power pellets, and then they allow us to eat the ghost, but only for a limited amount of time, right? It doesn't last forever.
Oh, good
So once I
point.
hit a big fat pellet, I don't get to do it for the rest of the game. It lasts for some amount of time.
For a limited time only.
Limited time only. And I don't remember if that time is fixed or if that time is random. I think it's fixed, but maybe not. And, there are different versions of Pac-Man that have slightly different rules, but those are the basic rules. So here's the exercise I want to go through. Now, obviously, and when I say obvious, I'm saying that to beat down anyone who doesn't think it's obvious, there are 4 atomic actions, left, right, up, and down, north, south, east, and west, just like in any other grid world. And that's pretty much what we're given. So here's the exercise I want you to go through. It's got sort of 2 parts to it. And this is actually an exercise that we have done with other people as a part of studies we've done. I want you to think about options that you might create here. Like if you were going to describe to a human being, here are the things you need to accomplish. Here are the things you need to do in this game in order to play it, and play it well, presumably. What kind of actions would you come up with? So I'm asking you to do the same thing that I asked you to do before, where you said, well, go to the doorway, and, that kind of thing. So I'm asking you to do the same thing here, but in Pac-Man land.
Sure, I could give that a try. I mean, I feel like in some ways this is harder than the other example because it was nice to be able to just navigate to that +1 and know that our task was complete. Here, there's a lot of things going on.
Yeah, but you're going to have to simplify it for me. And so abstract away, simplify it for me. What are the actions you would tell me to take? What are the things you would tell me to do?
There's like eating the dots.
Yeah, I like that. So that seems like a reasonable thing to do. Eat dot.
I guess the little dots versus the big dots, they might be 2 different things because I want to eat a big dot if I want to turn the tables on the ghosts and pursue them.
Right. Okay, so I'll just call the little dot dot.
Okay. And then I feel like it's really important to have a strategy for escaping from the ghosts or pursuing the ghosts, depending on the mode.
Okay, so yeah, so you might want to eat a ghost and you might want to avoid a ghost. Anything else?
I mean, I guess we could come up with more detailed strategy ideas, but those feel like the basic things.
Yeah, I think that pretty much covers it. And when we go back and we listen to the recording later, Michael, I think you'll find that this is almost exactly what you said when you explained how the game worked. You said you need to eat the little dots. And you also have to eat the big dots eventually because you need to clear them. If the ghosts touch you, then you die, so you need to avoid the ghosts. But if you eat the big dots, then you can actually eat the ghosts. And that's pretty much how you describe the game.
I see. So the way that I kind of thought about the game to convey it to people is at this sort of high level that kind of makes sense with respect to options as well.
Right, which is what I also think was true in the other grid world. Now, we could look at this and we say, well, these are options and maybe we can learn these options or they're given to us and somebody could code them up for us. I don't know. I want to point out a couple of things about these options, though, and this is going to bring us back to your excellent analogy about programming and about computing, which is if we think of these things as functions or procedures to execute, which I think is a perfectly reasonable thing to do, I want to point out that what we get from functions, procedures is not just the ability to reason at a high level, but we also get something called separation of concerns, which allows us to only think about parts of the world. So, for example, if you want me to multiply 2 numbers, I only have to worry about those 2 numbers. I don't have to worry about, the state of the stack or whatever else is going on in this program. I just need to worry about the 2 numbers you're asking me to multiply. So there's a similar kind of gain and abstraction that you get here by picking options carefully. So to illustrate this, I'm going to ask you to do one more thing. I want you to tell me, what are the states of this world? What are the features that make up the states in Pac-Man?
Okay, so it's definitely different if there's any dots left versus there's no dots left.
Right. So
That's an important distinction.
So the dots and where they are on the screen matter. So
you want, okay, so not an abstraction of the state. You actually want literally the things that make up the state.
Oh, well, which I claim is an abstraction of the state, almost by definition. So I think what you said before works in either case, right? So there are dots. There are dots on the screen. I need to know where all the dots are. And so there's some set of features that make up the state that tell me where dots are.
Right. Okay, so then there's where the Pac-Man is. The location of the little dots, location of the big dots, location of the Pac-Man, location of the ghosts. And I guess the walls aren't really part of the state in the sense that they don't really change. Though I guess if we were talking about multiple levels of the game, we might have to also say where the walls are.
True. I'm going to claim that you don't have to do that because it's all going to be taken care of by, you could, and there's nothing wrong with it, but it's actually all going to be taken care of by the transition function. Right, you can't enter walls, so you can't from a state go into where a wall happens to be.
Okay, and whether the ghosts are in I don't know what to call it, but power pellet mode, whether the ghosts are fleeing from us or whether they're attacking us.
Right. So we talk about scared ghosts.
Scared, whether the ghosts are scared. I see. They always look a little scared with the bulgy eyes.
Right. Not when they're coming after you, they don't. But when they start blinking purple and they're running away from you and screaming, ah, then they seem a little scared to me. Maybe that's just my version of Pac-Man. Anyway, so here's a bunch of features. And the details here, matter in implementation, but I think for what we're talking about don't, right? We talk about where the dots are. It doesn't have to be where the dots are. It could be where the closest dot is to you, or where the farthest dot is to you, or it could be every single dot and whether it's on or off. Same true for the big dots. Pac-Man, you have to know where Pac-Man is. You need to know where ghosts are. Maybe you just need to care about where the closest ghost is, whatever. And it does matter whether they're scared or not. In the same way that we don't have to keep track of the walls or other things that we might not have to keep track of, but whatever it is we're going to do in the detail, I think to solve the game, I think your reasoning is right. We need to know where the dots are of various flavors. We need to know where the ghosts and where we are, and we need to know whether we can eat the ghosts or not. And these features, however they're exactly expressed, are important for solving and planning in the game. Now, here's the observation I'm going to make. Just like when I ask you to multiply two numbers, I don't need to know everything else that's going on in your program. I suspect that is the case, that even though I need all of these features to effectively and efficiently solve a Pac-Man board, my options do not necessarily need to know all of these things. So, for example, if you told me to avoid the ghost, ask yourself whether it matters whether the ghosts are scared or not.
Interesting. Okay. Yeah, I guess if I am avoiding the ghosts, well, actually, yeah, it changes their behavior, so it may depend on that. Sure.
Right. So, I think we should delve into this a little more deeply, and the way I want to do that is with a quiz. Okay, Michael, so here's the quiz. I have here a grid, because we're doing grid worlds, and on each row I have the four little options you came up with. Eat the big dot, eat the ghost, avoid the ghost. And for the columns, I have the features that we came up with. I didn't put the Pac-Man feature up here because I didn't feel like it. I ran out of room, and I think you always need to know where you are. So I'm just going to assume that that's important. And I want you to tell me for each of these pairings, for example, the eat dot and the ghost pairing, whether I need that feature or whether it will be useful in order to execute a particular option. Does that make sense?
In principle, sure.
Okay, so for this very first one, if I want to eat the big dot, do I need to know where the little dots are? And so on and so forth.
Okay, all right.
All right, cool. Got it?
I think so. So am I doing things at the same time in a sense? Like when I'm eating the big dot, am I also responsible for avoiding the ghosts en route to that?
I want you to write code that will go and eat a big dot.
But it will fail if a ghost gets in the way, so I maybe do need to avoid the ghost as part of that.
Maybe. I will point out that you do have this little beta thing, which allows an option to be interrupted.
Okay. All right. So I'm not sure I perfectly get this, but I can take a stab at it.
Oh, I love it when you take a stab at things. Let's do that. You ready?
Sure.
Go. Okay, Michael, you ready?
Sure.
Give me an answer.
All right. So if I'm trying to eat a big dot, and that's really literally the only thing I care about, then where the big dots are on the screen matters to me a lot.
Yeah.
And I'm going to say the other stuff doesn't.
Right. I think that's right. Now, you made a point before we went through that Well, it matters where the ghosts are if I want to eat the big dot. But you didn't actually say you need to eat the big dot while avoiding eating ghosts. But by the way, unless the ghosts are scared, you can pick them up along the way. You could do that. And maybe that's okay. But you don't really have to in order to execute the eat the big dot option. And in fact, we'll see when we go through all of these that there's some sort of neat features that fall out of it. So let's just kind of take that idea that the only thing I strictly need to know besides where I am in order to eat a big dot is where the big dots are. I don't care where the ghosts are, so I don't care where the ghosts are. I don't care whether they're scared or not. And if I happen to eat some little dots along the way, that's wonderful. But if all I want to do is accomplish eating the big dot, then I don't really need to know where they are. Okay, so what about eating dots?
It still feels debatable to me because I feel like sometimes I'm driving and my spouse is navigating and she tells me, get off at this exit, but she means get off this exit while not hitting any other cars. So maybe two of these options can be active simultaneously, or do we have conjunctive options that somehow handle multiple things at the same time?
Let's keep that question in our heads for after we finish the quiz, because it's the very next thing I want to talk about.
Oh, okay. All right. So then I'll just use the strict interpretation then. So for eating dots, I need to know where I am, the Pac-Man, and I need to know where the dots are. But the other stuff doesn't matter to me.
Right.
To eat a ghost, I need to know where the ghosts are.
Mm-hmm.
Do I need to know whether or not they're scared? I mean, what does it mean to eat a ghost if they're not scared? Like maybe the initiation set of that option would prevent us from even having to care about whether or not they're scared.
Mm-hmm.
And so maybe we'll just leave it at that. And then avoiding the ghost, so it definitely depends on where the ghosts are.
Yeah.
And then I would argue that it also depends on whether they're scared, because if you're trying to avoid scared ghosts, they behave differently than non-scared ghosts. So knowing that they're scared makes it easier to predict where they're going to be.
Well, that would also be true for eating ghosts as well.
But again, I don't see how you can eat a ghost that is... You can avoid a ghost that you can eat.
This is true.
But you can't eat a ghost that can eat you.
Oh, that's a good point. So I think this gets us to a neat little point here, which is sort of what do these things really mean? I asked you, and you gave me kind of English descriptions. Eating a ghost may simply mean you can't eat a ghost if the ghost isn't scared.
Right, or it could also mean just collide with ghosts, in which case I agree that it's just like avoid ghost.
Right.
It's like the opposite of avoid ghost.
Yeah, and of course, by the way, even though eat ghost may itself not care whether you're scared or not, even if it doesn't make sense to eat a non-scared ghost, one could argue that that's all hidden inside the beta function, because I just have a probability of 1 of exiting if I ever enter a state where the ghosts are not scared.
Okay. All right. So I don't know, plus minus on those other boxes. I guess I would check scared for avoid ghost, but not for eat ghost, by my interpretation of those.
Which I think is fine. I probably wouldn't, and I'll tell you why I wouldn't. I wouldn't because avoiding ghosts, sort of in the kind of Markov decision sense of the world, here's the world where I'm now, basically involves you moving away from the ghosts. The fact that the ghosts are also moving away from you, isn't strictly necessary for accomplishing the goal of avoiding the ghosts. So you don't really need to know where they're scared, but a lot of it depends upon the details. So I would accept, I think, scared in either of these cases, and I'd feel pretty good about that. If we pop up a level, you can make a similar argument here, which you sort of made when you asked me that question, right? Asked me the question before we started the quiz, which is, well, if I want to eat a big dot, I need to avoid the ghosts along the way. So maybe eating a big dot or eating a dot really requires that I know almost everything, except, in the worst case, eating a big dot doesn't require that I know where the little dots are, even if I need to worry about where the ghosts are and whether they're scared or not. Although, if I know where the dots are, then I might choose to eat the big dots in such a way that I eat a bunch of little dots as well. But this is really a kind of, this points out two things. One, it sort of points out that if my options are not written in exactly the right way, then I may not be able to find an optimal policy. We'll talk about that in just a moment. But if I worry about that, then all of these options have to solve every single problem. And I kind of get nothing out of it. I don't get a big win by even thinking about it in terms of options, because effectively I'm just trying to solve the entire problem. The whole point of abstraction in kind of the software engineering and computing sense, and here where we're using it, is that in part it allows you to do an abstraction not just over time, it allows you to do state abstraction and other kinds of abstraction. So what do I mean by state abstraction here? Well, if you look at the eat big dot case, If I don't have to worry about where the dots are, never mind where the ghosts and whether they're scared or not, that means that if I needed to learn this policy, if I needed to figure out how to most optimally solve the problem of eating dots, I can actually ignore large parts of the state space. And what happens if I can ignore large parts of the state space, Michael?
Then you can solve the problems more efficiently.
Right. In the very beginning, we said the thing that made reinforcement learning hard is that as the number of states grew, the problem became more and more difficult. It was sort of superlinear in the number of states. So if I can avoid whole features of the states, that is, I can collapse states that are otherwise different as if they were a single state, where the dots are don't matter, then the problem of learning this policy, learning this option actually becomes easier, both from a planning point of view and from a learning point of view.
So it's as if the state space gets smaller.
Right. So temporal abstraction doesn't just buy us temporal abstraction, it buys us state abstraction, at least if we can divide the world up appropriately.
Neat. Okay. I mean, is there a guarantee that we can always do that?
No, there's not a guarantee that we can always do that.
In the kinds of problems that people can solve, maybe it's pretty common because people don't have infinite computational resources either.
Right. And in practice, I mean, if you just even think about the way you were just describing things, you sort of ignore large parts of what's going on around you in order to solve the problem. Right? We do these kinds of things all the time. It had better be the case that we can ignore large parts of the state space, because otherwise we're in trouble. It's going to be very difficult to move around in the world. I mean, first off, the world's a POMDP, so we're ignoring large parts of the state space anyway. But beyond that, I'm in this room talking to you. There are things going on outside I can't see. By and large, I can mostly ignore them, at least if for short periods of time. And we just have to hope in the real world that the parts of the state space that might matter, such as, I don't know, a polar bear, the location of the closest polar bear, it will be announced to me when that becomes relevant. And I can start paying attention to it. In which case, I'm going to stop worrying about eating my big dots, which is what I call teaching this class, and instead start avoiding ghosts, which is what I call running away from polar bears. So just to drive the point home a little bit, I just want to write down, sort of summarize what it is that we've talked about so far and how it all kind of comes together. And I think it's actually going to push us back to the very first slide. So we've done MDPs. We talked about SMDPs. We talked a little about what options actually do for you. And we talked a little bit about state abstraction before. This all brings us to a bunch of neat little facts. The first one is that because we are doing this SMDP type thing, because we are doing options, we get to inherit all of the optimality guarantees up to a point of what we had before in regular MDPs with regular actions. So in particular, we get all the convergence proofs, we get all the stability proofs. In other words, everything is all nice and well and good at SMDP land as it was in MDP land. There's a slight caveat to that, which is worth mentioning, and it's really what you brought up over the quiz, which is, well, if we don't pay attention to all these things and we live around in the option space, are we actually going to be able to really be optimal? Are we really going to be able to solve the problem? Do I need to know all of these things? And the answer is, well, if you got the right set of options in the right kind of world, then in fact, everything's good. But you cannot guarantee that if all you do is reason over options, that you will in fact end up with an optimal policy. We have another notion called hierarchical optimality. And that's the notion that given the set of options that you have, you can in fact converge to an optimal policy with respect to those options.
Okay.
Right, and I think that makes sense. And of course, whether you allow those options to pay attention to all of the state space also affects whether you're going to get the true optimality that you would have, or only a sort of optimality with respect to the particular set of options and the state features that you happen to be paying attention to. But I actually don't think this is a big deal, right? Because I think this is true for the problem in general. So I've got an MDP and I have a bunch of states. I made up the states anyway, as we've talked about before when we talked about POMDPs and PSRs. It's not clear these states actually exist in some very real sense. I came up with the state features. I described the way the world was supposed to be. There are clearly some ways of describing the state of Pac-Man that make learning easier and some that make it harder, some that allow us to be truly optimal and some that don't. Like if I came up with state features that only track the closest dots to me, I may not be optimal, But on the other hand, it might be easier to learn. And these are trade-offs that we make all the time. So in some sense, we're always dealing with a limited notion of optimality, which we define with respect to the set of actions we decide that we're going to consider and the set of state features that we're going to pay any attention to at any given time.
So in particular, once we've supplied a set of actions and a state representation, we would like agents to do as well as they can without necessarily questioning what we gave them. So in this case of temporal abstractions, again, hierarchical optimality is the notion that the agent should do the best that it can, respecting the high level or temporal abstract actions that they're given, without having to kind of question whether it could do better by not listening to that whole concept.
Right. And, so maybe it's the case that we should include in our options every single primitive action, every single atomic action. Maybe we don't have to do that. It really just sort of depends upon what you're trying to accomplish and what the trade-offs are. But we're making those trade-offs all the time, even when we define the problem in the first place.
I guess that's fair.
Right. But in the same way that once we have all the machinery of SMDPs in place, we might as well just pretend that we're dealing with MDPs for the kind of purposes of planning and learning. We sort of should do that with the set of options that we have and the set of state features that we have. So that's a big win, that we're going to still get optimality. It'll be limited by the set of options that we've constructed, but it was limited by the set of actions that we had in the first place. There's other things that sort of fall out from that. One is state abstraction, which we talked about before, that because we have these different options, if we are lucky or clever, we might be able to define options that don't require that we pay attention to the entire state and pay attention to everything that's going on. And if so, that can be a big win. But there's also something else, and I said this on the first slide. Because we're able to jump ahead from one doorway to another doorway, it allows us to avoid wandering around in, say, this northeast room, right? Which means we get to avoid what I'll call the boring parts of the Markov decision process, the parts of the state space that don't matter. Because remember, fundamentally, in order to do reinforcement learning, we have to worry about exploration versus exploitation. But the options, because they have these policies built in and because they're trying to accomplish very specific things, allow us to avoid having to pay attention to large parts of the state space. So they actually help us with exploration.
So with the idea that we can focus our decision-making energy on the places where those decisions actually have an impact, as opposed to stuff that really, there's only one right answer. We shouldn't be thinking about it.
Right. So in fact, the word that you mentioned, there's a phrase you used there that I think is just perfect, which is we need to focus on the places where we can actually make decisions. And because options allow us to kind of jump forward in time, it means in some very important sense from planning at that level, there are no decisions to happen here. We made the decision when we decided to execute the option, go to the southern door. How it gets there is its business. We're just assuming that it works. In the same way that when we decided to execute the up action or the left action, we didn't worry about what was happening while that action was being executed. We didn't think about it at all. Those are the decision points. That's what makes the decision process, and that's where we should be putting our computational energy. So insofar as we can jump ahead in the future, we can avoid making decisions, which means we avoid doing exploration, and that is a huge win. Let's delve in a little bit to some of the things that you've said in the last couple of slides. So I've brought back the options that we had before and the little pictures, and I erased a bunch of stuff, and then I made a change. Do you see the change?
You got rid of the word. Oh, yes. I was going to say you got rid of the word options, but you actually changed the word state into goal.
Well, that wasn't what it used to say in the title. It didn't say state abstraction, although I did write state abstraction at some point.
Oh, it had temporal abstraction.
That's right. So what I want to point out, you asked a question before we did the quiz. You said, well, wait, are these things all happening at the same time? Or are they happening like one after, how does this work? Well, you touched on something kind of neat there, right? Which is we have talked about so far this kind of options thing as if they're just primitive actions, right? You take one, then you take the other, you take the other. In other words, we've talked about sequencing. And that's perfectly reasonable, and that's really what we've been talking about in everything that we've talked about in this class. But when you ask whether the things could be running at the same time or whether we're trying to accomplish all these at once, we're really talking about something different, which is goals. So I'm going to claim that although we've been focusing on sequencing, which makes sense, right? We're talking about sequential decision processes, right? That's like the whole point of what we're doing. You could think about these things as running in parallel. Although we talk about, well, first I'm going to take the option of go to the east door, and then I'm going to execute the option, go to the south door, and then I'm going to go down, down, left, or whatever I'm going to do. You could conceptualize this as actually all the options are running at the same time. So I am always trying to go to the east door, the south door, the other south door, the other east door, and at any given time, one of them is in control. I mean, conceptually, that's no different, really, right?
Maybe. I mean, I guess it sounds like what you're describing is a little bit like a call stack in computer languages. The idea that, sure, while we're going after that first goal of getting to the east door in the northeast room, in the back of our minds is the idea that, well, the reason we're doing that is so that we can do these other goals next.
No, I don't. I actually mean something a little bit different. So imagine I had a bunch of things running in parallel. Like, imagine we had a thing called a computer, right? And the computer did many things at once. So it was recording, it was printing, it was letting some program compile in the background while the user was editing. From the computer's point of view, right, the way we think about these things is these things are all sort of running at the same time. But at least with respect to any individual processor, only one thing can be happening at the same time. So we can write down everything as if it's happening in sequence, but in some sense it's happening in parallel, or they're all fighting for resources at the same time, but only one of them can be in control at any given point in time. So even though the world is sequential, we think about executing an option, then executing another option, it's a reasonable way of thinking about the world, but there's another kind of conceit one could take, which is all of these things want to run. They all want to happen at the same time. They're constantly saying, take me, take me, take me. I want to have control of the mouse, or I want to control the screen, or whatever. And we're just choosing which one to let go. So they're still running at the same time. They're just not in control at the same time and aren't able to do anything. Once you do that, you end up thinking, or you can end up thinking about this problem of temporal abstraction as not one of sequencing things directly, but as one of managing competing goals. So maybe this becomes clear with an example. So if we go back to the Pac-Man example, at all times, you want to eat ghosts, eat dots, eat big dots, and avoid ghosts. They're sort of all happening at the same time. It's just at any given point in time, one of them happens to be ascendant.
Okay, yeah, that example makes more sense to me than the navigation example.
Sure, but I think conceptually they're the same. It's easier to think about it. In fact, we actually have a name for these kind of things. We call them predator-prey scenarios.
Who's we?
You and me. So here, there's
no. I don't call them that.
Yes, you do. This is a predator. Well, okay. The literature. The literature is replete with examples of things called predator-prey, where you basically want to go around eating as much as you can, but there's some predator who's trying to eat you. So you're always trying to eat because you have to eat, or otherwise you die of starvation. But you have to avoid the predator, or otherwise you die while the other one's not dying of starvation. And Pac-Man is just an example of predator-prey, right? Pac-Man needs to eat all of these things. Meanwhile, there are predators out there trying to eat it. And so there are kind of competing goals happening at the same time. I need to eat. I need to avoid being eaten. Right? And all of these are really examples of that. They even use the word eat and avoid in them. So I need to eat my food, and at the same time I need to avoid being eaten. And occasionally, because I live in a magical world where suddenly rabbits become as big as wolves, I can occasionally eat the wolf.
I see.
Right. But once you think about it that way, you can stop thinking about. I'm not trying to make a gigantic point here, other than we can think about actions as actions we're executing, or we can think about these options as things that are accomplishing goals. And this is where goal abstraction comes from in my title here. That really all of these options are about accomplishing different goals. You're trying to always accomplish those goals. Some goals are more important than others at any given point in time. And options, in fact, really make this sort of nice to think about because of beta. Because beta captures sort of the probability that we might terminate in a state. From this sort of goal abstraction point of view, you could think about this as either the probability that I've succeeded in executing that option, that is, I've accomplished my goal, or that another goal has become important and I need to interrupt whatever goal I was paying attention to at the time.
That makes sense.
Right. So I like this notion. of thinking about options or thinking about actions is always accomplishing goals and always sort of happening in parallel. Options are easier to think about than primitive actions that way because, in fact, when we define the options, I think we sort of naturally think of them as accomplishing goals. That's sort of the whole point. And primitive actions are sort of so low level, they don't really have, other than primitive goals like moving left or moving right, they don't really have big high level things that they're trying to accomplish. But options almost always do. That's why they're useful, and that's why people tend to come up with the ones they tend to come up with, or so it seems to me. And so when we think about managing goals, then we actually end up with a different way of thinking about this problem. And we move from a world where we're worrying about sequencing and hierarchical abstractions to a world where we think about managing and arbitrating between goals. Yeah, so let me write down different ways we might do that, because it turns out there's a whole subfield that worries about thinking about the problem this way. So as I noted on the last slide, right, once we start thinking about goal abstraction and sort of all of these functions or modules or procedures running at the same time, what you really have done is turn this into a problem of arbitration. By the way, this does have a name. I really like the name. It's called modular reinforcement learning. And that just sort of captures the idea that we've divided the world into a bunch of modules, or what we might call options, or what we might call temporally extended actions. And these things always have associated with them goals. They're always trying to do something or to accomplish something. They're different modules. And we're the operating system, and we need to decide which program we're going to let run next. And there are lots of ways you might imagine doing this. Here are three of the more popular ones, each of which has strengths and drawbacks. And they're kind of the things that you would come up with if you were given 5 minutes on a test to come up with something. So here are the various arbitration techniques. So the simplest one is greatest mass Q-learning, which, well, Michael, what do you think that means?
It means greatest mass Q-learning. So we have Q functions maybe for each of the individual subtasks, and we say, well, whoever's got the highest Q value gets to take the next action.
That's close. So the first thing you said is right. Since each of these things are their own little goals running around, they're like their own little RL bots or agents, then each of them has a Q function. And what greatest mass Q function does is it adds up all of the Q functions. So for the state that we happen to be in, add up the Q value for every state action pair, and whichever one is the largest, that's the one that we execute.
Wait, hang on. So I was saying whichever Q function has the largest value. You're actually saying which action after combining the Q functions has the largest value.
Right. So
it's sort of like they're voting.
That's exactly right. It's exactly like they're voting. So I say that the Q value of taking a particular action in any state is actually the sum of all the Q values for each of the agents indexed here by I.
And then
I just pick which
we
one.
go greedy.
Yeah, I pick the action that has the most mass across all the agents.
Okay. So then why is it Q-learn? Why isn't it just greatest action mass or something?
Well, the reason you have it as Q-learning is because you assume there was Q-learning going on, and you're using the Q function to determine how to vote. So that's exactly why it's called Q-learning, because there's a Q function involved. So this is adding everything up, and it does sort of exactly what you would expect. But basically, everyone votes, and whichever has the biggest vote wins.
So I want to say that the modules are voting, but they're voting on different actions, and whichever action has the largest number of votes wins.
Right. I'm sorry. That's what I meant to say. What did I say?
Okay. Well, it sounded like, it was interpretable as the whichever Q module gets the most votes gets to decide.
Oh, I'm sorry. Yeah. So that's actually closer to what you were describing.
Yeah, I know.
But yeah, so here all you're doing is you're voting for each action. That's the greatest mass Q-learning, and you just go from there. And that's neat and kind of makes sense if you assume sort of they're all care about some ultimate goal together. But people have observed that could be bad because it might not be good for any particular agent. Right? So imagine that I have a couple of, I have 10 agents, there are 10 actions, and each one strongly believes in a subset of those actions, but they're different ones, so each one believes in a different action. And so, or better yet, there are 10 actions and there's 5 agents, and there's an action that is the 5th choice of every one of those agents, but because it's the 5th choice of every one of those agents, it's the one that ends up getting the most mass. And so you haven't really satisfied any of the sub-goals.
Yeah, I mean, I could see that as being a bad thing, or I could see that as being a good thing, right? Because it's choosing that action not just because it's bad. It's choosing that action because it makes everybody a little happy instead of making some people really unhappy.
Right, but you can construct examples where sort of everyone's least favorite choice will still end up being the one with the most votes if nobody agrees on anything else. But that's okay. I mean, it's still, as you say, it's a reasonable thing to do under lots of circumstances. There just happen to be cases where it doesn't always work, which would, there's no free lunch. So it's not surprising that that's the case. The other alternative, or another big alternative, is actually top Q learning, which is what you described.
Oh,
You basically take whichever thing had the most associated with it,
the most value. Okay, yeah, good.
the most value. And that works pretty well. Again, those are the kind of things that you would probably come up with if you just spend a little bit of time. Just say, well, what are the obvious things that you could do? Both of those make sense. It, of course, also has a problem. And that problem is that the agent, well, there's several problems, but one that isn't necessarily obvious is the agent that happens to have given the most Q value to a particular action may also give very nearly the same Q value to all the other actions as well. So it doesn't actually have a strong preference. It just happens to have put high value on everything. And so you're not really doing much for it either. Meanwhile, every other agent might, for example, like the second action for that particular agent. And so it makes a lot more sense to take the second action, but you can't because by a quirk of fate, the other action got slightly more value to it for just that one agent.
So it starts to feel a little bit like a negotiation.
Right, which is why there's something called negotiated W learning.
W learning.
So this is a lot more complicated, and I can't write it down in just a fancy little equation like that. But what negotiated W learning basically boils down to is the agent with the most to lose gets to figure out what the action is. So you sort of minimize loss rather than maximize an average or pick the best thing. So you look at the subagent. That basically what you do is instead of looking at the things that everyone thinks might be good and averaging them or doing a max over them, you look at the things where the difference between the big choice, the maximum choice, and the minimum choice are really large, and let that agent make a decision. And you sort of weight it across all of the actions. It can be arbitrarily complicated, but basically you don't want any agent to lose as opposed to having agents win. And all of these have their strengths and all of these have their weaknesses. And they're all very kind of cool, and under different circumstances, greatest mass makes sense. In other circumstances, top makes sense, and negotiated is good for other situations. And you can come up with lots of other things. The key thing is that you need to do arbitration. The problem with all of these, though, all of these methods and any other methods that you come up with is that they're terrible. And in fact, they're impossible. What does that mean, you say? Well,
what does that mean?
I'm going to summarize it simply this. The very first example you gave, you said, or the very first response that you gave to me when I described greatest mass Q learning is you said, oh, what you're really doing is you're voting.
And voting is definitely not impossible.
But as you know, there is an impossibility result for voting. And that is Arrow's impossibility result. And if you don't know what Arrow's impossibility result is for voting, then you need to stop what you're doing right now and go look it up. What it basically says is that it is not possible to construct a fair voting system. The way that you can think about this in very simple mathematical terms that I know that I think you'll like, Michael, is that all of these things assume that everyone is using exactly the same units, right? But if one of the agents is using the metric system and someone else is using the imperial system, it turns out you can't even compare the two. There's absolutely no reason to believe that the values that each of these individual agents are developing follow the same linear notion of ordering of Q values. And if that's not the case, then all of these things are basically going to break because all of them boil down to doing what looks like some kind of addition or averaging.
Or maxing.
But maxing is just kind of a weighted averaging, right? Kind of an exponential averaging. And so you end up with a max that way. Same thing with negotiated W learning. You're subtracting things and taking mins. In the end, you're basically assuming that I can compare your 7 with my 7 and it means the same thing.
Right.
But why would your 7 and my 7 mean the same thing? So all of these have that kind of problem. And in fact, there's a paper that written by a student of mine that is a part of the readings that delve into this in more detail. And we could spend a lot of time on it, but actually the idea is very simple, which is really that once you start thinking about goals and you think about these individual modules or individual options as trying to accomplish different things, you have to deal with the fact that their goals may not be completely compatible with one another, and you have to come up with some way of making them compatible. And you can either assume that compatibility by just pretending your 7 and my 7 are the same, or you can say, well, there's some larger goal you're trying to accomplish that the arbitrator knows about, and the arbitrator is going to make decisions based upon whether it accomplishes that big goal. In the predator-prey case, for example, the big goal might be living long enough to reproduce. And so I'm going to pick the sub-goals that allow me to live long enough to reproduce.
I see, I think. So there's a high-level goal and then these sub-goals that are chosen to try to bring about the high-level goal.
Right. And so it's the arbitrator that has to decide what's going on. So this seems like a kind of straightforward thing, but I actually think it's kind of cool, right? That basically we went from actions to abstract actions, these options. Those abstract actions actually turn out to be, or at least one could look at it this way, ways of accomplishing goals. Once you have these ways of accomplishing goals, then suddenly you realize, well, these goals don't necessarily have to be compatible with one another. And so I have to deal with that compatibility. And so you've moved from an MDP with primitive actions to this larger notion of balancing trade-offs as you're trying to accomplish some large goal for the entire system. And in the end, they're still all MDPs because they're SMDPs and SMDPs are MDPs. And in the end, all of that reinforcement learning stuff that we've been talking about throughout the entire term still applies.
And you've kind of brought together generalization with multi-agent type of thinking.
Yeah, so we got multi-agents, we got single agents, we got multiple goals, we got conflicting goals, we've got abstraction, and this gives us scale, and everything's wonderful.
Hallelujah.
Okay, Michael, so, if you go all the way back to the very first slide, when we started this conversation, the slide said something about generalizing, but one of the words that was written on there was scalability. So one of the things that we've been talking about, sometimes explicitly, sometimes implicitly, is this notion of getting scale to actually happen. So just because I think it's important to think about scale more than in terms of abstraction, I just want to take a moment to talk about a kind of algorithmic approach to getting scaling to work that's different from just doing abstraction of the sort that we've done before, although it's going to turn out that all the things that we've done with our abstraction will actually work in this new kind of algorithmic view of scalability. That seem interesting?
Yeah, that would be really helpful.
Cool. Let's do that. All right. So here's a particular algorithm that I want to introduce. It's called Monte Carlo tree search. And there are 4 words there, and there's kind of 2 different parts. So for the beginning, I just want to concentrate on the tree search part and then tell you what I mean by the Monte Carlo part. So I want to use this picture on the right, this sort of little tree. All I'm trying to get you to think about with this tree is sort of what we've done in the past, say in an AI course, where you've got nodes representing states. There are actions that you might take that would get you to other states, and then more actions to get to other states, and kind of so on and so forth. But this particular tree has a nice little form that's kind of hidden by the edges and the nodes, and I want to sort of harp on that for a little bit. And I think it would help if you understand the algorithm that I'm trying to get through on this data structure. Okay, so the algorithm is written on the left, and it's a big loop, 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 loop. And it works like this. There are 4 steps. The first step is selection. And I'll define what all these things mean in but a moment, but I just sort of want to go through at a high level what each one is. So the first one is selection. And selection is basically the way in which you're going to decide what actions to take from a particular state. What's going to happen is you're going to take a bunch of actions, and eventually you're going to get to some point in this sort of tree here of possible states and actions you might see where you don't know enough to know how to make a selection. Once you're at a place where you don't exactly know how you should make a selection, the idea is that you're going to expand the tree there and then do simulation to figure out what it is you ought to be doing to make selections. And the way that's going to happen is you're going to estimate from that expanded set of nodes the true value of taking actions in those states, and then in a very kind of Bellman equation sort of way, you're going to back up what you learned through your simulation, and then that will allow you to select what to do next. And you'll just keep doing that over and over and over again, making selections where you know what to do, expanding, simulating the world for a little while so that you learn what to do and then make those decisions, and so on and so forth. So does that make sense at a very high level? This is what I'm trying to accomplish here.
Yeah, I think so.
Okay.
I mean, it reminds me a lot of other kinds of tree search that I've seen in AI classes.
Like what?
A star is a kind of tree search. Game tree search is a kind of tree search. They have similar kind of pictures where you repeatedly expand nodes and get estimates of values.
Right, and in fact, I like the game search one. This is not game search because we're living in an MDP and it's just us, and so we're not playing against an opponent. But something very nice about that particular one is the way it works in that world often is you have a particular way of figuring out what action to take, or you sort of expand and do a search among a bunch of possibilities, and then eventually you run out of time. And so you have to decide what the value is of whatever leaf nodes you've gotten to. And the way you do that is use something like an evaluation function, which tells you how good we think this node is. And that's just what you've got to work on. And you use that and you back up the values, and that helps you to make a decision about what to do. And then you make a decision, then your opponent makes a decision, you end up in a state, and you do it all over again. Basically, you search out as far as you have time to search out for. When you run out of time, you use some estimate that you got from somewhere of how good the node is, and then you back that up. And that's basically what we're going to be doing here, except we have another wrinkle. And the wrinkle here is where the Monte Carlo part comes in. So the tree search is very standard. The Monte Carlo part is, well, we've got randomness, we've got stochasticity in our transition model. And so we're going to have to come up with some way to do this estimation that takes that into account. And that's where the simulation is going to come from.
Okay.
All right, so let's sort of break that up into little parts. I actually, that's a lot of words, but I think kind of walking through this picture might help a little bit. So let's do the first stage. We're going to select. Well, how do we do selection in an MDP? Well, we follow a policy, right? So there's going to be some policy that we have. Let's not worry about where it comes from right now, but some policy based on experience that tells us what we ought to be doing in some state. So let's say, for the sake of argument, I'm in this particular state, and my policy tells me that I should take a particular action, and I take that action, let's say it's this one, and it ends me up in this state. Well, once we end up in this particular state, let's say the policy still tells us what to do, and it says, oh, take an action, and when I take that action, I end up in yet another state, and the policy says, well, from here, you should take a particular action, so I take that action, and then I end up in this state. Okay, so I have a policy. The policy tells me how to select what to do, what actions I should take, and it gets me through the tree until I get to a place where I don't know what to do. So at this point in the tree, and in fact, just so you know, the way I've drawn this tree, all the leaves of the tree are places where I don't know where to go next. I don't have a policy for it. I've got to figure out what to do. So here's what I'm going to do. I'm at this state. I don't know what to do next. I have to do something. So I'm going to do expansion, and then I'm going to do simulation. So here's how the expansion step works. From this state, I can take a bunch of actions, right? And from those actions, I can get to a bunch of states. In fact, I can just look at my transition model and I can see all the possible next states I might end up at based upon the actions that I take. And often that's what you would do. That's what you would do in a normal kind of game AI classical tree search. The problem here, of course, is that we might have many states. And so we don't want to expand out the tree that much. So instead of what we're going to do is we're going to kind of do a sort of sampling step. We're going to say, well, for each of the actions that I might take, why don't I take that action and then simulate for one step what state I might end up in? And then do that for another action, and then do that for another action, and so on and so forth until I have a few possible next state action pairs that I might see. And maybe that number is really small. Maybe it's 6, maybe it's 100. It sort of depends upon your state space. So I've done the expansion step. I've figured out where I might end up next, given all the actions that I might take. So I'm not drawing this because there's not a lot of room, but each one of these edges represents some particular action I could have taken, or I did take in my imagination, and the state that I ended up in, or what the nodes represent. And so each one of these edges has some action that's associated with it. I'm just not writing it down because of space. Okay? Mm-hmm. All right. So now I've got this. So I've now expanded sort of the fringe. Here's all the things that I might do and where I might end up next. And now I have to use that to kind of decide what I actually ought to do. Now, if we were doing the normal kind of tree search, like we talked about with game search, I would just use my evaluation function. But I don't have an evaluation function. So instead, I'm going to do simulation. And what that means is I'm going to follow some other policy. We typically have a name for that. We call it the rollout policy. And just for the sake of discussion here, let's just say it's a random policy. So I'm going to say I took this particular action, I ended up in this particular state, and then I'm just going to behave randomly for a while. And then I'm going to do the same thing here. Yeah, that looks random. I'm going to do that here. And then I'm going to do that here. And then I'm going to do that here. And then I'm going to do that here. And I'm going to do that here. And I'm going to get a whole bunch of spaghetti. Now, the spaghetti actually has nice little bits. I know, spaghetti's delicious. The spaghetti actually has all kinds of nice information associated with it. As I move through this path and through this trajectory by behaving randomly, say from this particular state, I actually see a bunch of rewards along the way, right? And I can just take that out as far as I need to, given my horizon, say, my discount factor. So I do this for a long time, and I collect rewards along the way. That gives me an estimate of being in this state and taking this particular action. And since I might take the same action multiple times and get to these states, I now can do a sort of average over all of these possibilities, get lots and lots of sort of estimates of this, and then that gives me an estimate of a Q value for each of the actions that I might take. So all I'm really doing is building an evaluation function by doing, well, Monte Carlo simulation from there. So I'm in this state, I took a bunch of actions, that gives me a concrete set of next states. From there, I just behave randomly for a while. I use that to gather a bunch of estimates of rewards. I add them all up, I average them appropriately, and now that gives me an estimate of the Q function. But by the way, it does more than that. Now that I have an estimate of the Q function for this state, backed up from here, I can actually back up information all the way to the top. And that updates the estimate of this particular node, and this particular node. So now that I have that, I backed everything up and I can just do selection again. Now this time around, because I've changed sort of my estimates of the Q functions along the way, I might want to make a different selection. And so that actually tells us where this original policy comes from. This original policy is just an estimate of Q values that I have, where I happen to feel very comfortable about those Q values. I've visited these states many times. I've backed up a lot of information from them, so I have a decent estimate, and I'm willing to do the kind of greedy policy that is implied by these Q functions.
I see. So we're taking greedy steps down the black part of the tree. When we hit a leaf, then we do the rollout policy, pi r, to get estimates of those different values. Do we now know anything new about the tree?
Yes, and in fact, if we did this, 100 bazillion times or however many number of times we sort of wanted to, we just can say, well, I know the actions that I can take from this node, and so I feel comfortable in expanding my policy all the way down to here for this particular node as well. And if I did this again, and let's say the selection algorithm had me go here, 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 and I got back to here again, I would actually know which action I wanted to take. Say it ended up with me being here, but then once again, I've gotten to a place where I don't feel comfortable about what to do next, and I would do the expansion and the rollout again, over and over and over again. So I just keep doing this again and 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 again. And what this gives me is an ever-expanding tree where I feel more and more comfortable about my Q values and therefore more and more comfortable about a policy that I should take.
And it seems like it's getting more accurate over time.
Yeah, and in fact, if you were at each of these nodes, right, and you took those actions and you did the expansion and you did that, let's say an infinite number of times, and then you did an infinite number of rollouts over and over again, eventually you would converge to a proper Q value.
Cool. That's interesting. So this is a planning algorithm. We need to know the transition model to be able to do those rollouts.
Right. Or you have to have some way of doing the simulation. So when you say you need to know the transition model, you could mean a couple of things. You can mean I actually have the transition model and I can do calculations with it, or you could just mean I have some way of simulating the world and I can just sample from it. So this is pretty neat, right? I think it has some neat little features to it. It allows me to kind of build up a model of the world, do a bunch of simulation and figure out what to do. But there are a couple of questions that should pop out to you, even though I kind of ran over them fairly quickly. I think the first one is, well, when do you stop? What is this actually? I mean, this is kind of an inner loop of a process, right? I'm at this state. I have an estimate of Q values that I'm comfortable enough in that I'm going to take actual actions following the policy that's implied by them. And then I'm going to keep expanding and learning more and more about it. Well, in principle, I could just do that for eternity. But at some point, you have to stop. And when do you stop? Well, you stop when you get bored.
And what do you do when you stop?
Well, once you stop, that's the next question. Well, what do I do after I stop? Well, you execute. You do a sort of one-step policy based upon what you've learned. And then you throw it all away and you do it all over again.
Wait, so you take you take that step in the world. Are you using the policy, the whole chain that you figured out?
Well, you could, but and in fact, sometimes you can do actually any number of things there. But sort of the simplest version of this is I started out with an empty tree. I'm in some particular state. I'm going to hallucinate all the things that I might do from there. As I do that, I'll be learning more and more about the world. This will allow me to do better and better exploration as I do this kind of Monte Carlo search and simulation and hallucination. And then eventually, I learn enough that I know what the right thing to do is from this state, and then I do it. And then I end up wherever it is I end up in the real world. And when I'm asked to do something again, I just do it all over again.
Wow. So it does a lot of thinking each time it takes a step.
Yeah, but it's very fast thinking because, I'm just flipping coins. If I have a fast simulator and I'm able to do addition pretty quickly and maybe some, averaging, I can actually do this estimate fairly well. What's going to impact this a lot is sort of how far down I can go before I run out of computational power. Typically, that's what bored really means. Bored means, okay, I've taken 15 seconds. That's too much time. Or maybe I've taken 3 seconds. That's too much time. It's time to do the best thing that I can based upon what I know. But if I can do that every single time, if I can expand this tree pretty deeply at every time step, then I lose 50 milliseconds. But 50 milliseconds is a long time for a computer and not any time at all for human beings. And the alternative would be to actually explore the entire space and try to solve the underlying MDP. And if you have a whole lot of states and a whole lot of actions, then that can take a very, very long time. So do you take 50 or 200 milliseconds every time you need to take an action and do it online? Or do you take 3.5 months of supercomputing power to figure out the optimal policy and then use that? And the answer is it depends. All right, one other question I'm actually kind of surprised you didn't ask me is what's this rollout nonsense?
Oh, I recognize that from reading about TD Gammon.
How is it the same?
The word actually comes from an understanding of how people figure out which backgammon boards are better or worse. They actually will. The rolling here is the rolling of the backgammon dice.
That's not at all what I was thinking.
What were you thinking?
Well, I was just thinking that we have some rollout policy, which tells us what to do when we're here. And I said, well, let's just act randomly. But I don't know why that's the right thing to do. I mean, if I end up here and I've got to do something, we're trying to get an estimate of this state and taking this particular action and ending up in this state. Why is that good or bad? And the way you're going to do it is I'm going to say, well, I know how good it is to be here by behaving randomly from that point on. That'll give you probably an underestimate of the true value, but it would be nice if you could do something that perhaps made a little more sense. So people who've done work on MCTS have often put some effort into, lots of things, being clever about this expansion, keeping the right set of statistics, kind of, shoving their exploration in very smart ways. But other people have spent a little bit of effort trying to figure out, can I come up with a better policy besides behaving randomly that will help me to have a better estimate of this particular Q value? And we could talk about it. I'm going to just quickly talk about one by mentioning something that we have already talked about so far in this lesson. Do you remember the commands you came up with for Pac-Man?
Oh, it was like eat, avoid.
Right.
So there was like eat little dots, eat big dots, eat ghosts, avoid.
Right. So I'm going to point out that of those 4, which I'll just call eat, and avoid, which one of those is different?
So I don't know. The first one,
eat,
where you're eating big dots, or small dots.
Okay,
no, I guess you want me to say avoid because it's the word that's different in the list.
Avoid is different, but it's actually different in a different way. Here we said, eat a little dot, eat a big dot, eat a ghost, and avoid ghosts. Remember when I said before that, temporal abstraction becomes goal abstraction? I'm going to claim that each of these does have a goal. One is to eat little dots, one is to eat big dots, and one is to eat little goblins. But that when you execute the eat small dot, it actually terminates. At some point, you eat a small dot, and now you can move on to the next thing. At some point, you eat a large dot, and now you can move on to the next thing. At some point, you eat a goblin, and then you can move on to the next thing. But avoiding goblins, avoiding ghosts, that isn't really something that ends. You're supposed to be avoiding ghosts all the time.
I see. Well, I guess it's sort of the negation. I do understand how that's different now. So, and eating the ghost ends when you succeed. Avoiding, I want to say, ends when you fail, right?
Right.
Like I'm avoiding the ghost. I wasn't able to avoid the ghost.
Right. So, in fact, these things have sort of goals. They have success conditions. They end when you succeed. Avoid is a little different. It sort of ends only when you fail. you can never succeed at avoiding ghosts. You can only fail at it in some sense. Whereas
I
here,
agree with that.
there's a sort of finite time in which you achieve your goal, and that's success. So it turns out that when you ask people to come up with these kinds of things, these kinds of options, they actually come up with things that look like this, lots of goals with lots of success metrics, but they also come up with things where you can sort of only fail. We actually have a word for that, and they're called constraints. So here you have goals you're trying to accomplish, sort of positive things you're trying to do, and then you have constraints. Basically, I want you to eat little dots, eat big dots, and eat big ghosts while honoring the constraint that I don't want you to be eaten by a non-scared ghost.
Okay, yeah. I mean, now from a logic standpoint, we've covered everything, success and failure, things that are defined by success and things that are defined by failure.
Right, but the failure here, right, in exactly that way. So why did I bring all this up? I brought it up because, one, I just think it's kind of neat that people actually come up with these things. But the other thing that I think is kind of neat is that it gives us a hint, gives us 2 hints actually, gives us a hint about how we might do a better job than just simply behaving randomly in our rollout policy. So here's something you might do. You might say, when I get down to here, rather than behaving randomly, and where, by the way, I sometimes will get eaten by a ghost, even though I could have easily avoided it, I'm going to try to behave randomly while still honoring whatever constraints I happen to have defined. So here, rather than trying to just walk around until something bad happens, I'm going to try to stay alive as long as possible, which is what this constraint tells me. And that's a different kind of rollout policy, but one that I claim that gives you a sort of better view of the goodness of this state. This state, action pair, is better because you can avoid violating your constraints for longer than if you are, say, in this state and take this action. And there are lots of other things that you might do. I just sort of wanted to give you a flavor of it, which is that I can use these sort of options if they are of a certain type in order to be smarter about the way I do my rollout policy. There's also another way that we can do this. I can still use options in general in this entire search up here before. Rather than taking primitive action and doing my search through the tree and my expansion, I can replace this with my actions with options as well.
Ooh.
And what's the big win there? Well, the big win there is by following the options, I'm getting deeper into the tree.
Yeah, I mean, it's the same kind of idea as in the option case that we talked about already. Except now we're in trees instead of, I guess, grids.
Yes, but trees and grids, it turns out they're all the same thing. So there's lots of things you can talk about here. There's been a lot of work in this space. Some of them are available as readings for the students. I recommend thinking about them. But what's, I think, kind of nice about it is that this general notion of treating solving an MDP not as just, I've got to solve the MDP, but as a kind of tree search problem where we take advantage of and use the randomness is something that unifies a lot of approaches that you might have.
Okay. Cool.
Okay. And I think that's pretty much, I'll say one more thing about this and then I think we're done. And that's just that there are lots of ways of looking at this. You might ask yourself, is this even reinforcement learning or have we just gone back to searching? And I'm going to claim it is. I'm going to claim it's a policy search algorithm.
What's your justification for that?
Well, my justification for that is I'm basically, by building this up, I am searching over possible policies. And what I'm doing in the inner loop of searching for policies is I'm doing a kind of reinforcement learning step here when I do my backups. And in fact, the way you do the backups is you use the Bellman equation as a way of re-estimating Q values. And once I have those, I now have another policy that I'm looking at, and I just keep doing that over and over again. So I'm really searching through policy space, which is sort of what the tree expansion is. And I have a sort of inner loop every time I run out of the, my confidence about the policy of doing a little bit of reinforcement learning to figure out what the policy ought to be. So it's sort of policy search with an inner loop of value iteration, sort of.
And policy evaluation, Monte Carlo policy evaluation somehow.
Right, exactly. Well, that's really what it is. And the way I'm doing the policy evaluation is by doing this, doing the Monte Carlo.
So it really combines a lot of ideas that we've talked about into kind of one algorithm. Has this been successful?
It has been successful. I've actually used it in my own work. It has this really neat feature that allows you to avoid searching over lots and lots of the state space. It's actually really wonderful. It actually has a couple of properties that are worth mentioning. So let me mention those properties, and then I think we're done. So I promised you some properties. There's a bunch of them. One of them is that it's useful, and that in particular it's useful for large state spaces. And the reason that that works, right, is that I don't have to actually look at all the states, do all of the value iteration for everything. I basically just kind of do it as I go along, and I only visit the states that I need to visit given where I happen to be in the world. There's some downsides of this, and one downside is depending upon just how much randomness there is in your transition model, you need lots of samples in order to get a good Q hat. But you know what? That's true anyway. If you have many states, then you're going to have to do a lot of visiting to figure out what's going on, usually. So this is the sort of, I think it's kind of intrinsic to the problem. Now, of course, if you don't have a lot of states, you still end up generating lots and lots of samples because of the way Monte Carlo works. Luckily, it's relatively inexpensive to do in most cases, at least most of the cases that we worry about. And in the end, despite all that, it has another good feature. I really like this feature. It's my favorite of its features, is that the planning time is actually independent of the number of states that you have.
Oh.
That's why it's useful for large state spaces.
I see. I mean, I guess if there's a lot of states, do we have to expand like a fixed percentage of them to know what to do?
Well, sure, you have to. That's how you're gonna generate your samples. You're gonna have to generate lots of samples that way. So yeah.
But then it's not independent of S.
Well, it is independent of S. That's one of the cool things about Monte Carlo tree search.
No, I know, but what you had said was what I asked was, so that means that as the state space gets bigger, do we have to expand? Or do we have to expand a fixed percentage of the state space?
Oh, you said percentage. I'm sorry. I didn't turn that into percentage. I'm sorry. So the answer is no, because if you did, it would depend upon the number of states.
Okay, but how could that be? How could it be that the state space gets bigger and yet we don't have to look at very much of it to know what to do?
Well, that's because you're really only going through, you're executing through the world. And the trade-off happens in the other bullet, which is the bad thing about MCTS.
It kind of reminds me of, like, I don't know, election surveys. That's probably not the right word. But this sort of idea that you can actually get an idea of how many people are voting, no matter how big the country is, by just surveying a fixed number of people.
Right, so long as they have properties that are consistent with that are representative. And so long as you can get a representative sample of the states and the actions, then you're good.
That's really interesting.
Right. Now, of course, that's going to depend on, so to me, what's going to drive that is going to be how much randomness and entropy there is in the transition function. Right?
I see.
Because if it's completely deterministic, you don't have to do a lot of samples at all.
Yeah, that would make sense.
But there's something else that drives how expensive Monte Carlo tree search is, which is the fourth bullet that I was about to write down before you asked me this complicated question, which is that the running time
is independent of the size of the state space.
It's independent in the sense that it's exponential.
Wait, in the size of the state space?
It's exponential in the effective horizon.
So you're saying it doesn't matter how many states are in the state space, but it does matter how far into the future you need to look to make a decision.
Yes. And of course, the tree itself is growing exponentially. So you're going to need to have more and more and more of those samples to make it work. Actually, due to Kearns and his colleagues, we actually know exactly what the running time is. It is big O of the size of your action space, which makes sense because that's your branching factor. And, I need another variable here. Let's call it X, which is how many steps you're going to actually run the thing for in that loop that I did before, raised to the horizon. Now, one thing that's important about the horizon is that the horizon isn't just something you make up, right? The horizon actually depends upon things like your discount factor. I mean, if you have a very small discount factor, then so far out in the future, it doesn't matter what's happening anyway. And so you can do better. But if you have a reasonable discount factor, then you're going to have to look pretty far out in the future to get a good estimate of taking a particular action in a particular state.
Okay, makes sense.
Right. So this is both good and bad, right? Monte Carlo is kind of neat because it's sort of neat on its own. It's very useful. It's one way of dealing with scale. It's completely compatible with options and other things that we know. It has a bunch of dials in it that we can play with that sort of help us and that we might be able to take cool advantage of. But you still need lots and lots and lots and lots of samples in order to make it work, which is true for any Monte Carlo method.
So is there a sense in which we traded, in big state spaces, we traded being exponential in the size, the number of state features, say, for instead exponential in the size of the horizon?
Yeah, and that trade-off is, it's right here, I suppose. This is our trade-off. And you're right. And that makes sense, right? So before, with the kind of algorithms that we've used before, you visit all the states, you back up information about them, and so on and so forth. So that clearly has to depend upon the number of states. Here, we're not worrying about the states. What we're doing is we're just looking forward into the future by doing simulation. And so every single time we have to look forward into the future, we have to look forward into the future. And perhaps we have to look forward very far into the future. And somehow, because we're doing this kind of Monte Carlo thing, we're doing kind of, I don't know, like almost a non-parametric estimate of whatever the true transition model is. That's going to require lots and lots of states and lots and lots of samples, and more samples the further out into the future that we go. So we are going to be trading that off. We're always trading off kind of space versus time in a particular way, and here the space is represented by the states, as opposed to the time, which is represented by how far out you're going to search.
Oh, that's nice.
Thank you. Okay, Michael, so I think we're done with this section, so it's time for you to tell me, what have we learned?
So this was the section on generalization and scaling.
Right.
So we connected that idea with function approximation, which was a section that I did.
Right. So we talked about generalization beyond function approximation.
To function approximation.
And beyond.
To function approximation and beyond.
Okay. And what kind of generalizations do we do?
So we did temporal abstraction.
Mm-hmm.
And in particular, we talked about temporally extended actions.
Mm-hmm. Or?
SMDPs?
Well, options.
Oh, right.
And SMDPs. And what does SMDP stand for?
Semi-Markov decision process.
That's right. Just like the truck.
Right. A semi-Markov decision process.
Exactly.
So it's an MDP with 18 wheels.
Yes. So we learned about options and temporal abstraction, which is really cool. And what else?
I want to say that led us to goal abstraction.
It did, as a matter of fact. And in particular, you remember?
Mediating between these different goals, competing goals.
We did, and that had a larger name. We talked about modular reinforcement learning.
Oh, right. I should remember that because I was alive when phones were modular. That was like a big deal.
Nobody was alive when phones were modular, Michael. In any case, one of the things that we got out...
I was alive before phones were modular, and I was alive when they switched to being modular.
You're such a hipster. Okay, so we talked about modular RL, or MRL as the cool kids call it, and the word you were searching for before, I think, was arbitration.
Arbitration. It just seems so arbitrary.
That's right. We talked about one other kind of abstraction, you might recall.
State abstraction?
Yes.
Oh, we got some state abstraction from the temporal abstraction.
That's right. But not only did we get some state abstraction from the temporal abstraction, that is, not having to pay attention to all states for all particular options, it actually turns out that state abstraction is sort of what function approximation is doing.
Okay. All right.
Right?
Yeah.
Yeah. So I think that's pretty cool. Was there anything else that we learned? I don't think so. Well, we had a name for at least temporal abstraction. We should at least mention that, if nothing else, that this is a form of hierarchical.
And we talked about quintessential search, but I think we actually meant quiescence.
We did. And what does quiescence mean?
Quietness.
Right. And in particular, it means that
in the search thing, it means that you don't have to, there's not all this crazy search and backtracking stuff happening anymore. Things have settled down and you can just, know exactly what the next thing is going to be. So everything is settled.
Right. And once things are settled, then you might as well not count it against your search. It has no more sort of exponential hit on your search. You are forced. We can treat it as almost as if it's a single move, say, or a single action, because once you do this, the next thing has to happen, next thing's happened, next thing has happened, and you're done. Okay, so I think that was almost it. Was there anything else?
Yes. We then made a leap to Monte Carlo tree search.
I wouldn't say it was a leap.
We climbed a Monte Carlo tree.
Yes, and did some search. And what did we learn about Monte Carlo tree search?
So it's really important to help with scaling because it lets you have computation that's independent of the size of the state space, even though it depends very possibly badly on the length of the horizon.
Right. So it's got a low O on the state space. In fact, it's independent. But it has a big O on the horizon, which I'll just call H here.
And it's exponential in that.
Yeah, in fact, it's exponential in
it. It looks like hydrogen now. So does MCTS and abstraction fit together in any way?
We could make it if we were abstract enough. See what I did there? If you pop back up far enough, you can sort of think of it as a kind of abstraction over actions and policies.
Well, no, I was thinking in particular that the idea that in MCTS, the way we talked about it, it was talking about specific states, ground level states. Like if we have a good way of abstracting states, can we use those abstracted states in an MCTS context?
Oh, sure. In fact, what I was about to say is that all of the stuff that we learned about generalization up here can apply to MCTS, some more easily than others. Doing the function approximation is sometimes quite hard, but not really because of the way that we're sort of thinking about the Q functions. But the temporal abstraction works very well because I can use options instead of actions to do my MCTS.
Oh, right. You even said that.
Yeah, I even said that. And as a result, the state abstraction and the goal abstraction can also follow through there if you think about each of the individual modules as doing their own version of MCTS. But MCTS is a very general notion. So if I were trying to decide between different modules that I might take, it will look exactly like trying to do the sequential decision making, and MCTS will work either way. But the big temporal abstraction is a huge win for MCTS because, again, all of its difficulty lies in the length of the horizon, right? So if I'm able to search far ahead in the future, that lowers my effective horizon.
Ah, nice.
Right.
So, okay, so if these ideas are so important for scaling up, do you feel like they've contributed to, I don't know, the ability of reinforcement learning to solve some real problems?
Oh, yeah, absolutely. No, these things actually come up quite a bit. They've been used in a lot of games. MCTS has been used, well, it's all in the papers that the students have read, but MCTS has been used to solve a bunch of game problems in just my own work as well as in a variety of other things. You probably know a few more off the top of your head. But really, anytime you have a huge state space or potentially a huge state space, these kinds of abstractions turn out to be extremely useful. Some of them are easier to think about than others. Function approximation is very nice, but does have its own problem with picking the right features, particularly if you're going to be nonlinear about it. Temporal abstraction is often quite useful because people can help you come up with things like options or constraints. Goal abstraction has a kind of similar flavor to it. And because of those things, the state abstraction helps. Basically, anything that lets you lower the number of states or the effective horizon has to make the reinforcement learning problem easier.
Oh, nice.
Right. So there, scalability. These things actually work. They actually are helpful. And this is a huge, wide open field in reinforcement learning. In fact, to your point, I'll just sort of end it with this, that I think that reinforcement learning has gotten so good at solving kind of well thought out grid-like problems that the field is really interested and increasingly more interested in figuring out how to make it work in the real world. And these kind of techniques, these abstraction techniques, these scaling techniques become increasingly important as you try to move it out into the real world. So this is a good thing.
Wow, I'm glad you told me about it.
I'm about helping others. So I think we're good. So I guess goodbye, Michael. Until next time.
All right. Yeah, see you then.